In this video, we're going to discuss the geometric series. And so the general form of a geometric series is you can have some constant a times some number r. And so I want you to notice the pattern here. I've got ar squared, dot, 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 ar to the n minus 1. So we just keep increasing the powers of r. R can stand for, we'll say for right now, some sort of like fraction. It can actually, we'll define it better, but for now, let's just think of it as that. So a geometric series could look something like 1/2, 1/4, 1/8, 1/16. So in this case, my r would be this 2 here, right? This is basically 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and so on. And then here, so notice now I've got a 7 on top, so that would be my a, so that's this constant that's being multiplied. And then notice what's going on with the denominator. I've got 3, 9, 27, and 81. But also, this is alternating in sign, which is totally fine. So both of these are geometric series. And so this is really what we're going to talk about in this video. So there's two ways that we could write a geometric series. We can write it with sigma notation, in which case the general form would be I go from n equals 1 to infinity, a times r to the n minus 1. Or if I were to go through and to expand that, that would be the series that I showed you at the beginning of this video. Now r, I said before it was a fraction, it's really called the ratio, and r can be positive or negative. So some geometric series converge, and we can actually find we can easily prove a formula for them. So let's do that. So I've got this partial sum of the first n terms of this series, okay? And so the first thing I'm going to do is I'm just going to multiply everything by r. So notice now where I had Sn, now I have Rsn, and now instead of a, I have ar, where I had ar, now I have ar squared, so on and so forth. Okay, so now that I have this, what I'm going to do is I'm going to subtract these two series from one another. So what I mean is I'm going to take these two series, and then I'm going to subtract, so I'm going to take this series minus this series, okay? So on the left side, I've got my s sub n minus r s sub n. And then this side, we just want to be a little careful. So notice, like as I look through this, so these ARs will cancel, and then these AR squareds are going to cancel. And so if you just think about how the pattern of this is going to work, so the only two differences between these two sums is really going to be this a and this ARN, because this only goes up to ARN minus 1. So all of that's going to cancel, and so what I'm left with in the subtraction is a minus a times r to the n. And so now this is all I'm left with, and so I can go ahead and factor. So on each side I can factor something out, and so on the left side I'll factor out the s sub n, and on the right side I'm going to factor out the a. Now I told you that we could find a formula for the sums, and so remember this s sub n it stands for a partial sum, right? So now in how I've set this up, I can actually easily solve for the s sub n by just dividing by that 1 minus r. And so here is a formula for any partial sum of a geometric series. So there we go. We've got our formula for the partial sums. But there's also something really cool in the fact that we have a formula for the partial sums. So you don't always get a formula for the partial sums. It can be very difficult to do with a lot of different series. But with geometric series, this is one where we can pretty easily figure it out with a little bit of work. And what's cool is since I have this partial sum formula, I can now evaluate this because n could be anything. And so, of course, the fun thing to do in calculus, right, is to ask that question, what happens as n goes to infinity? So we've got a, I've got this 1 minus r. So these things are just like stagnant fractions, right? They're not going anywhere. Where all the action is happening, right, is right here with this n. So this is the only place where there's an n. And so really it comes down to then, what is r? So r could be any number. So we actually have to break this into cases. So if the absolute value of r is greater than 1, if this is a number greater than 1, then what's going to happen is as n goes to infinity, this whole thing is just going to go to infinity, right? Because it's just going to explode in its growth. And so then the series is going to diverge. But If the absolute value of r is less than 1, then r to the n will end up going to 0. And so this is an infinite series, right? So if I have an infinite amount of terms, then if this is going to 0, then this just becomes a times 1 on top. So then I'm just really left with a as n goes to infinity. And so what's interesting is I get, for this geometric sum, I actually just get this nice little formula for as long as r is less than or equal to 1. The absolute value of r is less than or equal to 1. Now, why is that? Just in case you're not sure. So if r is less than 1, so just think about what's happening to the fractional values in this case. So let's say that I'm using 1/2 to the n. So I could start with 1. 1/2 is obviously way less than 1. 1/4 is less than 1/2. 1/8, 1/16, 1/32. So if I continue this pattern, there comes a point where the denominator is just so large that the value of the entire fraction is getting closer and closer to 0. And I just threw 1/3, 1/9, 1/27, so on and so forth, just so you can kind of see how that pattern works as long as my r is some number less than 1. So this is a super key formula then when we're talking about geometric series. And if r is greater than 1, then it just diverges, and then we can't find the sum because it's going to equal infinity. Okay, so let's put this into action then. So what we're going to do is we're going to write the first 4 terms of the sum just to make sure we've got it. And then we're going to determine if the series converges and to what. Okay, now one thing that can happen is you can mess with the index a little bit. So you'll notice that sometimes when you look at the definition, right, of a geometric series like here, so I start at n equals 1 to infinity. Starting at n equals 1 or n equals 0 is inconsequential when you're talking about an infinite amount of terms. But if we're just talking about those first 4 terms, then this is going to kind of impact the value. Now, just to make sure that you're reading this series notation correctly, of course, I'm going to suggest that you pause here and just write out the first 4 terms just to make sure that you're reading and interpreting this right. Hit play when you've done that part. Okay, so again, we're starting at n equals 0. So anything to the 0 power is going to equal 1. So that's partially why that was in there. And then this is negative 1 to the n. So that means each odd power will be negative, and then each even power will be positive. So this is the 0th power, the 1st power, 2nd, 3rd. So we alternate, and then we've got these alternating powers of 5. So these are the first 4 terms of this particular series. And then it will just continue. So just making sure that we understand what the series is saying. And okay, so now, does it converge? Well, I know that there's an n here and here, but the overall number that we're really talking about here is negative 1/5. So the fact that there's an n and an n here, it doesn't matter. You can just combine this into one fraction. So my r in this case will be negative 1/5, and then there is no a that we can see, so that means that a must just equal 1. And so once you identify your r and your a, the good news with a geometric series is then you can pretty easily tell where this is going to converge to because we have this nice formula. So very few series are going to have a nice formula, but this one does. So I just take my r equal to negative 1/5. Again, it's negative because this was negative. So I just plug everything in. And then when you compute everything, so you ultimately end up in the denominator with this 1 plus 1 over 5, which will give you 1 over 6 over 5, and then you can just flip this to get 5/6. Okay, so there's more than one way to kind of work with the geometric series. So for instance, I could just give you a random series, and so this is kind of why writing out terms is helpful, just to kind of start getting this in your brain. So we want to determine if the following series converges or diverges. And I think what can be helpful here is to rewrite this using the sigma notation. So I would challenge you here to just see if you could write some sort of formula for this, and then hit play when you think you've got a formula. This is a really great exercise just to check in on how you're understanding series notation. Okay, so I'm going to show the formula. Now there's more than one way to write this, but I decided to start my formula at n equals 1 to infinity. And so I need this first part to be positive. So this is going to be an n plus 1, because then that'll be squared. This will be a negative. And now if this is squared, then 3 squared is 9 and 2 squared is 4. So there's more than one way to do this, but you want to make sure and double check that whatever sum you wrote actually comes out to these terms. And now that I've written my sum like this, I can much more easily tell what is going on with it. So I can see here, my r is this -3/2. And so since r is now a number greater than 1, the absolute value of it is a number greater than 1, boom, it diverges. We don't have to go any farther. So that's why it's kind of helpful to have this, because then you can really easily pick out your r. Okay, now the other thing I want to talk about is just a couple of rules in general for series, which can come up with geometric series. So if I have two series a sub n which equals a and b sub n which equals b, so that means I know that these converge. If I have two convergent series, then there's a couple things I am also allowed to do. I can sum them, and I'm allowed to break up those different sums, and I know that those two different sums will equal the same things that they converge to beforehand. So I can sum them. I can also take the difference of them, and in taking the difference, I can split these up into two different differences if I want to, or I can just take a minus b, whatever they converge to. The last rule is there's the constant multiple rule. So if I have k times a sub n, I can factor that k out, like you see here, and then this just becomes k times a, and this is true for any number k. Now, there are two consequences of this. First of all, every non-zero constant multiple of a divergent series diverges. So what that means is if I know that a sub n, the series a sub n diverges, then if I multiply that by some number k, it's still going to diverge. So that's one thing. And the other thing is if either of my series diverges, so if one series diverges, a sub n diverges and b sub n converges, then both their sums and their differences will still diverge. So you can't undo that. So once one diverges, the whole thing diverges. Okay, so that being said, so we can go ahead and we can kind of mess around with some of our geometric series. And so I can really break this up right into two separate series, as you see here. So what I would recommend is that, we've talked about a couple of these, and I didn't put the index in here, so sorry about that. Let's just assume that it goes from n to infinity, but I've broken these up. I just want to give you a chance to use that geometric series formula if you can. So I want you to take a second to evaluate both of these and just check in with yourself and then hit play when you're ready. Okay, so in this case, so my first series, my a will equal 5 and my r will equal 1/2. So if I just plug that in, so what I'm going to get is 5 over 1 minus 1/2, and so I will get that this will equal 10. And for the other one, so now my a is 1 and my r is 1/3, so I'll have 3/2 ultimately for this other sum, and so then I can just combine those two to get 11.5. And so that is another way that we can evaluate convergence. We can break it up if we need to. All right. The last thing I want to talk about is I want to talk about how geometric series can actually apply to repeating decimals. So the question here is to express the ratio, to express as the ratio of two integers. Okay, so this is actually just a geometric series in disguise. So specifically, I can break up this repeating decimal. So this is in the hundredths, right? And then this repeats. So we could say this is the 1/100th squared, and then this is in the 100th cubed. So I can just keep that going for forever. So now that I see this sum, I can actually kind of play around with it and rearrange it a little bit. And what I notice is that every single term has a 231 over 100 in it. So I can go ahead and factor that 231 over 100 out. And so look at what I'm left with now. And so this part you can see clearly as a geometric series, and then this we're going to just treat as like a constant to multiply by. So I am going to just focus on this part for right now. So as this part is written, my r will be 1 over 100 and my a will be 1. And so I can just plug this straight in, 231 over 100 times my little geometric series formula. And so ultimately what I get is that this is going to equal 231 over 99. So that is expressing it as the ratio of two integers, right? So this is another way that I could write that repeating decimal. Okay, so that's everything I want to tell you about geometric series. And one thing I do want to say, this is one of the few series that has this nice formula for the sum. So geometric series are usually one of the first infinite series that you learn about because they're the easiest and the nicest because they have a nice formula. Usually we can't figure out what the sum is. So usually we just want to know if a series converges or diverges because the sum is going to be too difficult to find. Okay, and I am going to leave it at that. So I will catch you guys in another video where we'll talk more about different types of series. But for now, bye-bye.